All right, so in this example, we're going to find the distance from a point to this equation. So at this point, you should be recognizing this as the equation of a plane in R3. So we've got that standard form, ax plus by plus zz equals d. So this is a plane. Even if it doesn't tell you that, you should recognize that as the equation of a plane. All right, so in your textbook, there is probably a formula with a box around it for finding distance from a point to a plane. If you really want to memorize formulas, you can do that. My advice, though, is to just sort of think this through. Think about what you know in terms of dot products and cross products and the right triangle that we've labeled, and use that knowledge to help you figure out what the formula should be for that. Otherwise, it can become kind of unwieldy trying to memorize all these different formulas. So I'm going to just draw kind of a generic picture, not necessarily this specific plane and point, but just a generic picture of a point and a plane. So got some plane here and some point that is not on the plane, and I want to find that distance from that point to the plane. So you'd be measuring a perpendicular distance from the point to the plane. However that's oriented in space, turn your viewing angle so that you're viewing it so that you can think about that perpendicular distance from that point to that plane. You could measure the distance to the plane at lots of different points, but you'd want that shortest distance, which would be perpendicular. So that's relevant. So that's where we've got a right triangle involved here. We also might think about kind of the information that we have and that's easy to get from the equation of the plane. All right, so this is the distance that I want. And thinking about the right triangles that we talked about, so we had some right triangles with some vectors and some distances. And we had one side labeled with a cross product and one side labeled with a dot product and some relationships there. So that's essentially what we want to generate here, so that this would be one leg of our right triangle. And there's a couple different ways that you might draw this, but you might also think about kind of what information is easy to get from this equation of a plane. So one thing that's pretty easy to get from that equation of a plane is a vector that is perpendicular to this plane. So we started by deriving the equation of a plane from a vector perpendicular to the plane, but then we've been exploiting the idea that you can work backwards from that. These coefficients, when it's written in this standard form, these coefficients of the x, y, z terms give you the components of a vector that is perpendicular to this plane. I'm going to label that n for a normal vector. So 1, 2, -4 would be a vector that is perpendicular to this plane. So whether it's pointing that way or the opposite direction, we can turn it around if necessary, and it could be longer or shorter. Another thing that's very easy to get from the equation of the plane is a point on the plane. Right? The point would just be any x, y, z coordinate that makes this equation true. So you can write down a whole lot of different points on the plane. The point that you find may or may not be the point that is closest to your point, other point that's given, so it could be just some other point somewhere else on the plane. So I'm going to just label that B. So we could find some other point on the plane. An easy one to find here, if I put in 0 for y and z, then x is going to be 12. Right, so a vector normal to the plane, any point on the plane. So I just picked some easy numbers here. Infinitely many other combinations that you could come up with that would give you points on that plane. But again, remember that that point probably is not the point closest to the point that you're interested in finding. Once you have a couple of points, it's easy to find a vector between the 2 points going either direction, BA or AB. And so I've got several different vectors here. What I want to think about is how I can sort of rearrange this picture a little bit to look more like the picture that we've been drawing and labeling with dot products and cross products. And so I'm just going to use some symmetry here. Notice that this distance d, if I just square things off here, this distance d, make a parallelogram, would be the same as if I measure that over here. So if I extend this and measure that over here. And so if I draw my normal vector over here, and I have my other vector being BA, the way I've drawn that, So I've got my n vector and my vector BA. What I really want is this side here that's along n. So that's the adjacent side of my triangle here, where there would be the angle theta. So I just translated this vector over. Remember that this normal vector is the same direction and magnitude. It's the same vector no matter what initial point I draw that vector at. Okay, so it's a matter of kind of connecting the picture where you've labeled the sides of the right triangle to what's happening here, and then being able to think about those two, the side that you want and how to use the vectors you're given to get that. All right, so it's the adjacent side of the triangle, which is labeled using the dot product. So in general, when we've been labeling these before, we maybe called this vector V and this vector W, and this adjacent side would be the absolute value of the dot product divided by the magnitude of the vector that you're projecting onto. So the magnitude of my vector W. So that's the adjacent side, and that's what we need here. Okay, so the distance that we're after here for the picture that I have here would be the absolute value of AB dot n. Here's my n vector. I don't have my AB vector written down yet, but we'll find that in a second, divided by the magnitude of n. And this probably does not look like the formula that's in your textbook, but you'll notice that if you do the calculations that are here, or you do the calculations that are in the formula that's in your textbook, they're really the same calculations. It's just a matter of whether this is written as a dot product or an expanded form of what that dot product represents. Okay, so we've got our vector n. It's easy to calculate the magnitude of n. I've got my point A that we were given to start with and my point B over here. Need to find my vector AB, or actually in my picture here, this is BA. So BA. So let's go ahead and do it the way I have here in the picture. All right, so BA would be the vector that starts at point B and ends at point A. So if we start at 12 and end at 1, we've got a decrease of 11 units in the x direction. And if I start at 0 and end at 2 in y, I have an increase of 2 units. And then in the z direction, I have no change. So there's my vector BA. We can do BA dot n. So just the dot product of these two vectors. At this point, that calculation should be pretty straightforward here. So 1 times negative 11 will be negative 11, plus 2 times 2 is 4. Plus negative 4 times 0 is 0, so we get negative 7 for that. All right, so here on my numerator, I'll be taking the absolute value of negative 7, and then I'll divide that by the magnitude of my n vector, so I'll go ahead and do that calculation over here. Magnitude of n will be square root of 1 squared is 1, plus 2 squared is 4, plus negative 4 squared is 16, so square root of 21. Okay, so the distance that I need over here is going to be the absolute value of negative 7, which would just be 7, divided by the magnitude of n, so square root of 21. So if I simplify that by taking that absolute value, 7 over the square root of 21 units. Okay, so again, my advice is not to memorize those formulas in the textbook. There are enough formulas that you do have to memorize. These are probably not the best use of your time to memorize formulas. My suggestion is to be able to think it through, be able to label this right triangle, and use the right triangle to figure out whatever it is you need for the distances you're going to be asked to calculate. The other thing I want to point out about this example is that I have a lot of vectors and a lot of calculations here, none of which are very difficult calculations. But I've tried to label each step here so that my vector is labeled. I don't just have a vector here not labeled. I have a calculation here, it's labeled what that is. One of the things that you'll find both in this chapter and the next chapter is that you're going to be doing a lot of fairly easy calculations and then kind of putting them all together to get an answer that you need. And so the better your habits are for keeping your work organized and labeled, the better the chances are that you're going to put the right numbers in the right place at the end to get the correct answer. It's really common that students grab the wrong number and put it in the wrong part of their calculation at the end. So try to make sure your work is organized, steps are labeled so that you can reuse those calculations in later things.